Hello and welcome to the workshop Control Your Burn, a look at natural gas process efficiency in industrial applications. We have Mr. Art Womack with us, who will be the presenter for this workshop, and I am Steve Craig, the moderator. Art has been a regional sales manager for Fluid Components International, FCI, for the past 14 years, and working in the instrumentation process control industry for the last 24 years. Before we begin the workshop, there are a couple items to mention. Feel free to post a question in the control panel on the right-hand side of your screen. We will have a Q&A session at the end of the workshop. You will receive a copy of this recording of this workshop within 24 hours. You will also receive a post-workshop survey, and we appreciate your input on that. And also, we will conduct 3 interactive polls during the presentation, and we would appreciate your participation. We have also posted 3 handouts in the control panel that you can download. One is the 10 essentials of specifying flow meters. 2 is best practices, actual gas calibrations. And number 3 is the best practices engineering guide on how to install and select a flow meter. With that, I'll turn it over to Art.
Thank you, Steve, and we do appreciate everyone attending today. For the workshop, there are a few things we're going to cover. The first thing we're going to look at is, some of the industrial natural gas applications that we see commonly. We're going to take a look at 4 natural gas process efficiency considerations, go through an overview of thermal mass flow meter technology and how it can meet your needs and your natural gas measurements, and then followed up with a Q&A session. Hopefully at the end of this, we'll see that we all have a greater appreciation for the potential cost benefits that come from a properly instrumented system. So when it comes to industrial processes, experienced instrument and control engineers and technicians will agree that the use of natural gas as a fuel source continues to grow. Applications can be found in practically every industry segment, as we've illustrated here. Natural gas consumption can be a significant part of an organization's operating expense, whether it be burner control systems monitoring the stoichiometric ratio of air and natural gas, or steam boilers that are required to meet varying demands. Efficiency improvements can be achieved and quantified with the proper selection of your flow instrumentation. Many times we are not dealing with ideal metering conditions for one reason or another, which could negatively impact our natural gas flow measurements. As part of the workshop, we will look to understand common issues and how they impact our process efficiencies.
Okay, at this moment, we'll take a brief poll, a moment to provide a question. We would appreciate your interaction during it. And all you need to do is touch the circle for the answer. So the first question is, what is your primary efficiency consideration when selecting natural gas flow metering technology? Please select one of the following: accuracy and repeatability, natural gas composition, process conditions variations such as flow, temperature, and pressure, or improving energy efficiency. So I'll give you about 10 to 20 seconds to go ahead and enter your selection. And the poll is closed. So now we will take a look at the poll results. And it appears that accuracy and repeatability is the #1 selection. Number 2 is process conditions, variations such as flow, temperature, and pressure, followed up by improving energy efficiency and natural gas composition. So Art, I'll go ahead and let you take it away.
All right, thanks, Steve. Thanks everyone for participating. You know, like yourselves, we see that accuracy and repeatability, changing process conditions are a key component of, your natural gas measurements. And part of this workshop, we're going to go into some good detail as to how we can address those areas. So breaking down the 4 efficiency considerations we're going to take into account today, we want to look at energy efficiency, knowing how changes in our mass flow of the natural gas impacts our calorific value. We're going to take a look at the gas composition itself and what impact, if any, does a change in the composition percentages have on our overall efficiency. Process conditions and variations. Am I able to actually measure my flow of natural gas under all operating conditions? And accuracy and repeatability. Can I rely on my flow measurement to help optimize the efficiency of my process? So looking at energy efficiency and trying to achieve that perfect burn where we use the full calorific content of the natural gas source, is we're tied into basically the mass flow of the fuel and the ability to achieve that perfect burn. It is feasible a lot of times to reach efficiency numbers in the mid to higher 90s. Given varying process conditions, we need to measure the mass flow in order to better understand the BTU content. So as we look at the efficiency based on the energy input versus output, trying to achieve that 80, 90, 100% value, we can look at a boiler as an example. Here we have the energy in being our fuel, our natural gas, and basically we're looking at the lower heating value or lower calorific value as a measure of available thermal energy produced by a combustion fuel. In contrast to the HHV, or the higher heating value, the LHV considers energy losses such as energy used to vaporize water, although its exact definition is not uniformly agreed upon. One definition is to subtract the heat of vaporization of the water from the higher heating value. This treats any H2O formed as our output as a vapor. The energy required to vaporize the water, therefore, is not released as heat. LHV calculations assume that the water component of a combustion process is in vapor state at the end of combustion, as opposed to the higher heating value, which assumes that all of the water in combination and all of the water in a combustion process is in a liquid state. Ideal operation occurs at the stoichiometric point. The highest efficiency occurs in the zone to the right of the SP that you can see there in the middle. Operation to the left of the SP results in incomplete gas combustion and production of carbon monoxide with a greatly lowered efficiency and presence of unburned gas in the flue gas. Operation to the right of the stoichiometric point results in excess air, which is heated by the flame. This heat is carried out in the flue gas, resulting in efficiency loss. The excess oxygen also results in an increase in NOx production. So here, ideally, we're trying to get that efficient burn where we use all of our fuel and then we minimize our emissions. Second consideration we want to look at involves a component breakdown of natural gas. Natural gas composition varies per location and installation. All parts of the world have some variations associated with it. In some instances, you may see some seasonal changes in the composition as well. For an accurate flow measurement, the actual natural gas composition is an important consideration to select and calibrate the natural gas flow meter. These differences in composition will also impact the calorific value of the fuel being burned. By properly addressing these variances, we can ensure that our flow measurement is optimized and maintain the appropriate air to natural gas ratio. When looking to achieve our maximum efficiencies, there are technologies that have the capability of storing multiple calibrations to optimize performance. In many cases, input from a gas analyzer can be used to switch to a gas composition that best represents the existing process conditions.
Okay, everyone, let's take another moment for the second poll. And the question is, which technology provides the greatest flow turndown ratio? Differential pressure multivariable, thermal mass flow meters, vortex, or D, none of the above? So I will give you another 10 to 20 seconds. If you would please join us in selecting one of the four. Okay, the poll is closed. Now let's see the results. More than half selected thermal mass flow meters, and that's correct. Differential pressure multivariable, we'll discuss that and the turndown ratio along with vortex in this workshop. But thank you for your input, and Art, I'll turn it back over to you.
All right, thanks, Steve. So the folks that answered thermal are correct. When you look at the technologies available and applications that have varying demands, such as those that have very low flow pilot conditions to keep a piece of equipment in a standby mode, compared to the need to ramp up for 50% or more capacity, understanding your turn down range is very important. So properly sizing and selecting for these conditions requires clearly defined minimum and maximum flow values. As the above graph illustrates here, there's a significant difference between the more common technologies used. The standard flow range turn down of a thermal flow meter often exceeds the optional turn down range of other technologies such as vortex and differential pressure or multivariable measurements. And also you got to look at the velocity capability or the velocity range capability of these technologies as well, knowing that there's limits on the upper and lower limits achievable by each. So when we look at accuracy, the question we ask ourselves, why settle for less? As stated in our polls, customers are looking for the best accuracy of these measurements as possible. And when you look at different manufacturers, different technologies, a lot of what you're going to see published is their base accuracies. These are under ideal conditions. And given that, a lot of times we don't need that custody transfer level measurement, looking for accurate, repeatable readings without breaking the bank. So with thermal, commonly you'll see a 1% of reading and a 0.5% of full scale is a typical accuracy under ideal conditions. Repeatability of the measurement is also important when looking to maintain that proper air to natural gas ratio, with a 0.5% of reading being a typical value. These accuracies are well in line with that of common meter technologies used for the air measurements as well, allowing us to maintain that optimum ratio for that efficient burn. Other things you got to take into account with different technologies is the fully developed flow profiles. When we calibrate an instrument, it's under ideal conditions, and we've got to keep that in mind. So we're looking to calibrate for either that laminar or turbulent flow, depending upon where I'm at in my flow measurement range. From that perspective, a lot of times you're looking for 20 diameters upstream, 10 diameters downstream, to give you that straight run that's going to allow for that fully developed profile to occur. Another component that's often overlooked is the use of inferred variables in our flow measurements. Many times a density is assumed without the meter technology actually going on a calibration stand. In some cases, a lower cost air calibration is performed and then a linear correction factor is applied to offset those differences in gas densities. Depending upon the technology used, these equivalencies do not always take into account the thermophysical properties of natural gas. Another issue you may see is that changing process conditions are not always accounted for when a density is assumed, leading to an incorrect measurement of the actual methane content of the natural gas feed. There are also industry standards that confirm that the best practice for calibrating a flow technology takes into account actual gas and actual process conditions. In this standard for thermal mass flow meters in Section 8, it's clearly stated that the best practice is to do an actual gas calibration under actual conditions when at all possible. Natural gas calibrations add some incremental costs, but those should easily be outweighed by the added confidence that our readings are accurate and reliable. Here's an example just to give you, an idea of what the differences might be based on these thermophysical properties. If you look on the left hand of the screen, the error percentage is shown for different gases compared to an air baseline. And in this case, we're looking at natural gas versus air. And if you look at that, there's a great error, just associated with those differences in the properties. And on top of that, if you were to overlay those lines on top of one another, a linear correction is not just going to be a perfect fit here. You've got some discrepancies at the low end. You start getting some nonlinearity between the two curves at the higher and mid range, and all of these lead into inaccuracies in our measurements.
Okay, Art, thank you. And we have our last poll, everyone, and we'd appreciate your input on it. And the question is, what are two commonly recognized mass flow meter technologies? That's talking about an instrument, a flow meter, that provides mass flow with no external input. Is it vortex, Coriolis, ultrasonic, differential pressure, or thermal mass? And I will give you 10 to 20 seconds to provide input. And I see people are still entering the data, so I'll give it a couple more seconds. Okay, the poll is now closed. And the results of the poll are 71% selected thermal mass flow meters, 63% selected Coriolis. As it turns out, both those do provide mass flow. And then 19% selected differential pressure or vortex, and then ultrasonic with 8%. So Art, I'm going to turn it back over to you.
All right, thanks, Steve. So yeah, like Steve stated, when you look at the difference between mass flow technology and volumetric, there are two commonly recognized flow meter technologies for mass flow. Looking at the first group of products here, this is your differential pressure, your multivariable with different type of flow elements, your vortex, ultrasonic, and such. All of these technologies are looking at volumetric flow rates. So to account for mass flow, it is required to do that pressure temperature compensation. You know, with this temperature pressure compensation at standard density, all of that information can be computed into a mass flow reading, but inherently they are volumetric devices. So when you look at mass flow meters, thermal dispersion Coriolis recognizes that, because the way the sensor technology works, there's no need for that additional pressure temperature compensation to give us that mass flow output. So let's take a time just to look a little bit at the breakdown, the construction of a thermal flow meter. First, you've got a couple different types, one being the insertion meter, which you'll commonly see for 2.5 inch and larger line sizes. Insertion meters being easy to work with when it comes to installing and piping that already exists, from a maintenance standpoint, not needing to have bypass systems in place if you want to take an instrument out and service it or have it recalibrated. The other side that you'll see is an inline type or a spool design, and these are commonly in 2 inch and smaller line sizes. Construction in both is going to be a thermal wells, fully welded with the RTDs positioned within them. One of the areas that you really look at having that calibration done in the small line sizes in a spool piece just gives you that added accuracy and confidence that when it's installed, it's going to be working properly. You don't have variations due to rotational effects of not properly being installed or not properly centered. You also eliminate some line blockage that could lead to inaccuracies. So there is a benefit to that spool and smaller line sizes. The basics are simple. You've got two RTDs. One of those RTDs is going to have current pass through a heater to create a temperature differential. The unheated RTD is just referencing the process conditions of the gas that we're measuring. So essentially we're creating this delta T. Within thermal technologies, there's a couple of different ways to drive it. One is constant power, where you put a fixed current into the heater and then create a delta T at no flow. And as the flow increases, that differential temperature will get smaller. The other method of doing this measurement is with constant temperature or constant delta T. Now in this case, as flow increases, we're going to continue to put more heat into that sensor to maintain the temperature differential. And both of these methods, we're looking at, the delta T in the case of constant power being proportional to the mass flow of the gas, or in the case of a constant temperature unit, the current being used to maintain that temperature differential is proportional to the mass flow of the gas. And there are some newer hybrid technologies that combine the benefits of both into a single device. In this case, we have a device that's operating as constant temperature in the lower flow range, providing us a faster response time, which is good when we're trying to really maintain our air to natural gas ratios. The other ability you have is to achieve even higher flow capabilities, is it switches over to a constant power mode that then allows us to continue measuring delta T at higher velocities. So with this, again, we're looking at the cooling effect of that sensor, and that's tied into the velocity of the gas as well as the density of the gas. So based on our pressure temperature changes, that is going to impact our gas density, which will directly impact the cooling effect on that sensor. And in this case, since we're automatically adjusted for this change in pressure and temperature, we can provide one instrument with a mass flow output. As such, the mass flow technology, is really the best for controlling those balances, because you can truly balance your air oxygen content of your air to that of your heating content of your natural gas. And when you look at the simplified mass flow equation for a thermometer, we can see that density and velocity play a great role in that mass flow output. So what we'd like to do is look at a couple of conditions, one being when we have changing pressures in our system. In this case, we're going to look at, natural gas under an atmospheric pressure, basically giving us an output of roughly 500 kilograms per hour. Then we're going to increase that line pressure. We're going to have that process condition variation. In this case, we're going to double the pressure it's in the line from 14.5 to 29. And we're going to see that that actually is a doubling of our mass flow rate. So we're actually 2 times higher in mass flow than we would if we were just doing a simple volumetric measurement. And again, tying back to our basic equation, these changes in density, the cooling effect of having more molecules flowing past that sensor or less molecules if the pressure drops is all taken into account in the thermal mass flow measurement. The other area you look at is changing temperature conditions. So under the same conditions, we're just going to look and see how an increase in temperature affects our mass flow reading. So in this case, an increase in temperature is going to result in less density of our gas. And we can see just a small 70-degree change is going to almost reduce our flow rate about 80% of what it was. So without taking into account these changes in process conditions, you're really not going to get the full understanding and the full measurement of your calorific value of your natural gas as you're trying to balance your readings. And again, this is supported through our simplified equation where that change in temperature is going to affect our density. So all of this is accounted for without any additional instrumentation. We talked a little bit about insertion type meters. There's some benefits here with regards to installation, maintenance. With these type of devices, we do have the ability to hop tap existing piping. That way we minimize the need to shut down processes. We minimize the need to put in more expensive bypass systems, saving costs in that area. Benefit of the technology for insertion type is, using some type of adjustable compression fitting or packing gland. These allow us to insert through the hot tap process an isolation ball valve and possibly remove for inspection, maintenance, recalibration purposes. And here's some examples of what that would look like with a meter installed through a ball valve with a packing gland, and a little closer up look at the packing gland assembly itself. So with that, you might see an installation where you have a flange mounted isolation ball valve, full port, allowing for the OD of the sensor to pass through it when it's open. To remove this from our system for maintenance service, all we have to do is loosen the nut on the top of the packing gland. Then we are in a situation where we can now extract that flow element through the ball valve assembly itself. And basically there are ways of managing for safety purposes how this is accomplished. So some technologies, some manufacturers have fittings that the sensor itself is secured, will not come out of the fitting. Others might use a chain or a guard, but we definitely want to make sure we fully extract outside the ball valve itself before we close it to ensure that we've not damaged the sensor and we're fully isolated. Now at this point, we can remove that flow element from the process for any work we want to do. Briefly want to touch on some additional considerations. A lot of times, again, we're dealing with less than ideal installations. We might be putting a meter in an area that was not originally designed for a meter run. So our upstream, downstream conditions are limited. There's ways to address that through use of flow conditioners. There's different types of flow conditioners on the market. So in a lot of cases, we need to understand, how that instrument needs to be calibrated for that particular design, as well as an understanding of permanent pressure loss based on the different types of flow conditioners available in the market. Site-specific requirements might be in place for hazardous areas, so we have to look at selection of explosion-proof or non-incentive instrumentation to meet the needs of the site. And a lot of that is going to be backed up by third-party certifications. You'll see this with your manufacturers. And another area that might be coming into play is the need for failure rate data to complete analysis of safety functions as related to a safety instrumented system. In this case, you're looking for your manufacturer to provide you that data necessary to complete your calculations and overall analysis. We see this in play with more and more of these natural gas applications. So just coming to an end here soon, having always done something a certain way doesn't mean there's no room to improve. As engineers and technicians, it's important for us to understand the available technologies so we can make those informed decisions regarding which provides the best results for a given application. When multiple options are available, it is best to dig deeper into the total cost of ownership, not just doing things the same way as before. So in brief summary here, energy efficiency. We want to look at ways of optimizing our natural gas to oxygen ratio. For gas composition, we want to understand our impact on the calorific value, and this typically is going to require that mass flow measurement so we truly understand what that value is. We look at turn down and other application conditions, the ability to measure both high and low flow conditions, not being limited, on the technology, truly suiting the technology to the application. Accuracy, we want to watch out for equivalencies. Best practice is always to do an actual gas calibration when available. And then our last other considerations, take the time to look at installation maintenance requirements. Meter runs, do I have enough room for a fully developed flow profile? And then any site-specific safety requirements or application-specific safety requirements that I need to meet.
All right, thank you, Art. That was a good session. And now we're going to open this up for question and answer. If you want, we will keep the question section open so that you can enter it, and we'll answer them in order. Art, I do have one question that's popped up. How much pipe straight run is required?
That's a good question. Again, ideally we're looking for these fully developed flow profiles. Our experience has always been 20 diameters upstream, 10 diameters downstream without any obstructions. It allows for that fully developed flow profile, whether it be turbulent or laminar. You start shortening that distance and you're having an impact on your accuracy, and it can change greatly depending upon what's upstream of the metering point as well as downstream. So you really need to take into account all those conditions. There are ways to address it through flow conditioning. In those cases, you might be able to work in areas as small as 9 diameters. But again, we need to analyze that full meter run or the full process conditions so we can truly understand what the impact on the accuracy is going to be, and whether it's something that we need to do to, whether we need to take a step to improve that accuracy.
Okay, thank you. And we do have a couple more, Art. We'll move on to the next question is, do most flow meter manufacturers use actual gas calibrations?
That's a great question. Experience has been that not every manufacturer has the capability to do an actual natural gas calibration in-house. There's a lot of times you might see again, an air equivalency used with a equivalency factor applied to it, which will have some additional inaccuracies to it. There are times where somebody might just use methane as the calibration media. That gets us closer to the natural gas content, but there's still some slight inefficiencies, related to the thermal physical properties of the gas that introduce some inaccuracies. So it's really something that customers need to explore with the manufacturers as to how they're going to perform these calibrations and really have an understanding of the accuracy of a meter, regardless of the technology, given the calibration media used.
Okay, thank you. And the next question. The question is, I understand that there are two types of thermal technology, constant power and constant temperature. Which one is best for natural gas applications?
When you look at the two different types, constant temperature and constant power, both have been utilized in natural gas applications for decades. There are some slight advantages to the constant temperature and the constant, or not the constant power, but constant temperature and hybrid type designs where you've got that faster response time, especially if you're trying to maintain a air to fuel ratio. Having that faster response time means you're not getting lags that might affect your efficiencies of your process. The other thing you've got to look at when you take into account response time, the technology being used, we're just looking at today at natural gas. We also have to look at the air side of the equation, make sure that response times are similar for the device being used, that they're both looking at mass flow. That way they maintain that ratio and you don't have one leading or lagging the other with regards to the response time.
Okay, thank you, Art. The next question. Does the meter need to be calibrated during installation?
That is a good one because, when you look at various technologies, a lot of times you're not doing a field calibration of your instrument. These technologies are being calibrated at a stand at the factory. The benefit of having that calibration in natural gas under your actual process conditions is that once that instrument's in the field, we know what the line sizes are, we know what the gas composition is. We have a high level of confidence that once that meter's installed in the system, there's no reason to do a field calibration. It all ties back to the capabilities of the manufacturer and the qualifications of their labs, whether they're traceable to NIST or ISO standards.
Thank you. And the next question. What is the response time for thermal mass flow meters?
Good question. The response time is going to vary, again, depending upon how you drive that sensor. With a constant temperature or hybrid design, you're typically going to see a single time constant of about 1 to 2 seconds. When you look at constant power, that time constant gets to be a little bit larger. You might start seeing time constants in the 9-second range. So again, if we're really looking for efficiency and tight control, there is some benefit to that faster response time available through constant temperature and hybrid designs.
Okay, thank you. And the next question. What is the smallest pipe diameter that we can measure on?
It varies by technology, but with thermal meters, we have seen line sizes as small as a 1/4 inch, up through 2 inch for spool type designs. So common, probably more in the 1 inch to 2 inch range, but we can go much smaller in line size with a thermal device. And again, it's something you really need to explore with the manufacturer to understand what some of the limits might be with that.
Okay, we've got time enough for one more question. And this is a good one. How does the external analyzer input work for gas composition changes?
So speaking for ourselves, if we have a meter that we have maybe 2 or 3 different natural gas calibrations in there, and those calibrations could be related to differences in gas composition, differences in, maximum flow range requirements under certain conditions. We can put several curves into the unit. And based on the input, typically here we're looking at the gas composition. So say our baseline's 90% methane, 10% ethane, and the composition changes seasonally to 95.5. We might have those two curves in there. And then based on a measurement from your gas analyzer, you might see that, current conditions are leading you to one of the curves. So from an analog input to the meter, you can actually define windows for which curve to be used based on your gas composition input. So it allows you to just automatically switch back and forth between the appropriate curve when you have changes in that composition. Hopefully that was clear enough.
Okay, we're going to answer, we're going to do one more. We've got enough time. Question is this FCI gas fundamentals similar to the airflow FCI mass flow meters? Let me look at that one more time. Is this FCI mass gas fundamentals similar to airflow meters?
Yeah, if I understand this correctly, the fundamentals, we're looking at here really apply to all gas measurements, whether it be natural gas, air, flares, biogases. It really applies to all. You need to take into account your gas compositions. You need to take into account your actual process conditions. Understand what your requirements are. But the principles apply to all of them. Regardless of the gas, this technology is going to give you a mass flow output. No need for additional pressure temperature compensation. And
okay, thanks, Art.
Again, in these examples, monitoring the mass flow of your air is just as critical as monitoring the mass flow of your natural gas if you truly want to keep your balance going. So principles apply to both.
Okay, we're going to close the Q&A session, and moving forward, if you have an application or project and want to discuss it in more detail with Art or I, feel free to put in a quick message in the question section on the control panel, along with your phone number or email, and we will get in touch with you as soon as possible. Or you can contact us directly. And the information for Art, A. Womack at fluidcomponents.com, and Steve Craig at stevec@fluidcomponents.com. So in conclusion, thank you, Art, for the presentation of today's workshop. You did a great job. And thank you, everyone, for participating. Have a great rest of your day. Thank you.
Thanks, everyone.